Hello everybody. So in this video we're going to talk about Norton equivalent circuit and the relationship between Norton equivalent circuit and Thevenin equivalent circuit. Okay. So let's start by stating what Norton equivalent theorem says. It's Norton equivalent theorem or Norton theorem. Uh, it says that if you have any circuit, let's see, if you have any circuit with two terminals A and coming out of two wires coming out of it, and let's label the terminals A and B over here. So no matter what's inside, all the components in here could be either voltage sources, current sources, resistors, and they could be connected in any order and in any which way. And the sources could be dependent or independent. So it's basically a very generic circuit, right? And Norton theorem says that any such circuit, you can replace that circuit with a circuit which looks like this: a current source in parallel with a resistor. Okay, and remember the Thevenin theorem also said something similar, that any generic circuit you have, if there are two wires coming out of it, you can replace that with a voltage source and a resistor in series with it. Okay, but Norton theorem says that you can replace that with a current source and a resistor in parallel, right? Again, so that's somewhat of an involved theorem. We're not going to prove it, but we're just going to start assuming that you can actually do that. Okay, means any such circuit, you can replace it with a circuit which looks like this. So now that we assume that we can do that, then our next goal is to calculate what IN should be and what RN should be. Or for example, if you're in a lab and you're given a black box and there are two wires coming out of it, and you're asked, okay, hey, calculate the Norton equivalent circuit of this. So how would you do it, right? So now, well, a key statement in the Norton theorem is, okay, when I say, replace this circuit with this circuit, what do you mean? That means if I replace that circuit with this circuit, these two circuits behave in exactly the same way. That means if there's anything else connected here and the same thing is connected here, when you replace this part with this part, nothing in here changes, right? So as long as this part of the circuit is concerned, nothing changed if you replace this whole thing with a simple circuit. Okay, so that's what it means by saying we can replace one circuit with its equivalent circuit. Okay, all right, so that means what we're saying is the circuit on the right hand side behaves exactly the same way as the left circuit on the left hand side. So that means, let's say if I short circuit this and measure the short circuit current, and if I do the same thing here, since these two circuits behave exactly the same way, I should measure exactly the same current, right? So now if you look on the right hand side, if I short circuit this, the voltage drop across the resistor is 0, right? That means the current flowing through the resistor is 0. That means all IN should flow through if you do a KCL, if the current going down is 0, then the entire IN should go through the short circuit here, right? So that's the easy way to measure IN. So first, the way you measure IN is short circuit current, ISC, is equal to IN. Okay, short circuit current. Okay, so now we know how to measure IN. Okay, the next question is, okay, how do you measure RN? Okay, so let me get rid of this. Okay, so again, notice that if on the right hand side circuit, if I don't connect anything to A and B and measure the voltage difference between A and B, the voltage difference would be equal to IN times RN, right? Because the entire current IN is going through RN. Therefore, the voltage drop from top to bottom will be IN times RN according to Ohm's law. So that means if I do the same thing here, I don't connect anything and just measure the voltage drop. If you don't connect anything and measure the voltage drop between A and B, then that should be equal to IN times RN, right? And therefore, from that, you can easily measure RN because you already know IN. So second point is you measure open circuit voltage, and then Rn would be equal to open circuit voltage divided by short circuit current. Okay, VOC is open circuit voltage. Okay, it's that simple, right? So if you're in the lab, you're given a black box and asked to measure the Norton equivalent, you first, well, hopefully you don't short it. You actually, connect a resistor, and then to be on the safe side. But if you really don't care about burning stuff, maybe you just short circuit it and measure the short circuit current, and you say, okay, that is my IN, right? And and then you don't connect anything, measure open circuit voltage, and then you measure Rn. Okay, so note that you could do similar calculations by connecting, instead of shorting this, you can connect a resistor R, and then derive everything in terms of R, and you can do that too. You don't necessarily have to short circuit, but if you do short circuit, these calculations will be easier, right? IS is equal to IN, you get a straightforward answer. Okay, so at least if you want to do theoretical calculations, you can still do this. And in most cases, you could, in practical cases, it would be safe even if you short it, right? Because there will be some sort of internal protections, and there will be some sort of internal resistance. So it's okay to short in many cases, but again, I think you can use your judgment. Okay. All right, but if you want to be on the safe side, you put actually a resistor in there, a resistor between A and B, instead of shorting it, and then you do some more complicated calculations. Okay, so here I'm just showing you the simplest way to do that, right? Okay. Okay, so now let's look at the relationship between Thevenin equivalent circuit and a Norton equivalent circuit. Okay, so we said that given any generic circuit, like that, we can replace that with a circuit which looks like this, using the Thevenin theorem, or a circuit which looks like this using the Norton theorem, right? And we are saying this circuit behaves exactly the same as this circuit, and then this circuit here behaves exactly the same as this circuit, right? So by equivalence, then these two circuits would also behave exactly the same way, right? If they are representing the same circuit, then these two circuits should also behave exactly the same way, right? So then, okay, given that's the case, can we get any relationship between if a circuit looks like this, and if the circuit which looks like this, and we are saying these two behave exactly the same way, then we're asking, okay, what should be the relationship between all the quantities here, right? If these two circuits behave exactly the same way, what should be the relationship between the quantities? So let's look into that, right? So if these two behave exactly the same way, let's say if I short circuit on both sides, and then let's say the short circuit current here is ISC1, and the short circuit current is ISC2, right? So both these circuits, if they behave exactly the same way, then ISC1 should be equal to ISC2. Okay, so ISC1 is VTH divided by RTH. So let me use black for this. So VTH divided by RTH is ISC1. This should be equal to IN. Okay, so we have this relationship between VTH, IN, and RTH, right? Okay, and okay, so let me keep my notations consistent here. Okay, so this should be V capital TH, R capital TH, and IN. Okay, all right. All right, so we have one relationship here, right? Okay, so now we short circuited and got a relationship. Let's open circuit and see what the equivalent relationship would be. Okay, so I'm gonna erase this stuff here, erase this stuff here. All right, so now I'm saying if I just keep it open and measure the voltage here, let's say open circuit 1, and measure the voltage here, open circuit 2, these two, open circuit 1 should be equal to open circuit voltage 2, because we are saying these two circuits behave exactly the same way, right? So in that case, then on the left hand side, open circuit 1 will be equal to VTH, right? Because the current flowing through RTH is 0. There is no drop across it. Therefore, the voltage drop across A and B should be equal to the voltage drop here. Okay, so that's VTH, and that should be equal to the open circuit voltage on the right hand side, which will be IN times RN. So which implies VTH divided by RN should also be equal to IN, right? So if you look at these two equations, this implies RTH is equal to RN. Okay, so what that means is in the resistor in the Norton equivalent circuit and the resistor in the Thevenin equivalent circuit, they're equal. Okay, that's what that means. And two, let's call this is equal to R equivalent. And now that we have R equivalent, and then we know the Thevenin voltage should be equal to Norton current times R equivalent, right? And this R equivalent is the same resistor in both the circuits, right? So now we have a complete relationship between all these quantities, right? So this is one way where you can see this relationship. Let's look at another way, right? On the left hand side, we are saying we have this this Thevenin equivalent circuit. Let's say this is RTH and VTH. And on the right hand side, we have this Norton equivalent circuit, Rn. Okay. All right. Again, so let's see if you want to measure R equivalent here, right? So remember the way we said if you want to measure R equivalent, the equivalent resistance, basically you want to put all sources to 0, right? Or we said this is zeroing out, right? Zero out all sources. So if you zero out all sources, that circuit, zeroing out this voltage means shorting it, right? That means the voltage drop here is now 0. And it's like this. This is RTH. And the equivalent resistor looking in will be equal to RTH. Okay. Now, if these two circuits behave exactly the same way, if we zero out all sources in here and then look at R equivalent, we should again get the same thing, right? So if you zero out all the sources, then the current source will be open, right? Because now the current here is 0. And you have Rn. And then if you look at the R equivalent looking in, this will be equal to Rn, right? So again, if these two circuits are the same, then the R equivalent resistance should be the same, and then you get RTH, which should be equal to Rn. Okay, and that's the equivalent resistance. So we just saw two different methods, two different ways to see that the resistor in the Thevenin equivalent will be the same as the resistor in the Norton equivalent. Okay. Right.